In this example, we're going to determine the resultant force in 3 dimensions. Now, we're not just going to determine the resultant force, we want to also determine the direction angles of the resultant. Now, we're given 3 forces, so we have F1, which is 6i plus 3j minus 2k, and these are all forces, so our units are in newtons, so kilonewtons. We have F2, which is negative 4i plus 5j plus 4k, and F3, which is 2i minus j plus 3k. Now, what happens here is each force is expressed using vector components along the x, y, and z axes. So if I'm to just write this out, so our forces, so F for forces, is expressed in terms of their components. So we have the x components, so xi plus yj and plus zk. So these are known as our vector components. Similar to when we do 3D vectors, we have the x and the y components, or the vertical and horizontal components. It's the same thing that we have here looking at. Now, what we have to do in this context is to first of all sum our components. So that's what I'm going to do now. So right here is where we're looking at, and we're going to sum all the components for the I vector, or along the x-axis. So for our resultant along the x, what we have here is 6i in F1 right there, and we have negative 4i for F2 and plus 2i for F3. Now 6 take 4 and plus 2, that leaves us with 4i. So then on to the y components for our resultant. So now we're just looking at the j values, the coefficient of the j values. So what we have here is 3j, and that's coming from F1, and the j value for F2 is 5j. And just in case you're wondering where these numbers are coming from, I'll just circle this column here, and these are my j values. So we're now at 5j, and the last one there is negative 1j, or negative j. So when we do our 3 plus 5 and take 1j, we're left with 7j. And then on to the z components. So rz equals, so this is now us looking at the final column. So let me just clear this bit so you can track where we are. So it's these components that we're going to now sum. So the first one for F1 is negative 2, so negative 2k, and plus 4k, and plus 3k, and this gives us 5k. So what we have now is the components that we need to put together our resultant vector, which is what we're going to do next. So our resultant vector, so r, and this is our vector symbol, is going to be equal to our 4i and plus our 7j and plus 5k. So these values is just what we have up top here. That's what gives us the resultant vector. So that represents our resultant vector. What we're going to do next is to find the magnitude of our resultant. Now, to find the magnitude of our resultant, we use 3D Pythagoras' theorem, which is really similar to what we normally use for right angle triangle. All we're going to do is the square root of our 4 squared, which is coming from our resultant vector up top, so this 4, and then plus that 7, the coefficient of the j value, that's where this is coming from, so plus 7 the whole squared, and plus 5 all squared. And you notice I have a tendency to put these in brackets, and that's because sometimes when you're working with negative numbers, if you don't bracket based on what you have for the components, the vector components there for the resultant, if you don't bracket, some of the times your calculator will give you incorrect answers. So I've always just practiced to bracket these because it's the safest way. So our resultant here, the magnitude of our resultant here is 9.49. And this here is in Newton. So 9.49, it's actually kilonewtons here for our unit. So that right there is the magnitude of the resultant, and the magnitude really represents the strength of the resultant. So what we're going to do next is we're going to find the direction angles. And these angles that we're going to work out, they describe the orientation of the vector relative to each of the axes. So relative to our x-axis, our y-axis, and our z-axis. So what we do now for our angles, so for the first vector component, for the I component, we say cos alpha. It's really the direction, the cosine directions you'd see this as, or the direction cosines. So it's cos alpha equals 4, and this 4 is coming from the resultant vector here, where you see that 4i, and it's going to be 4 over the magnitude that we have here, which is 9.49. So as you can imagine, if you're going to find the angle here, I'm just going to write, therefore our angle is going to be cos inverse of what we have there, which is 4 over 9.49. And this is what you put in your calculator to get the angle that we're after. So when we do cos inverse of 4 over 9.49, what we have here is 65.07 degrees. So this is 65.07 degrees. So that's the first angle. I'm just going to make some space up top to do the rest of the calculations. So the next angle, so that's cos beta, so that's in relation to the y-axis. So we have 7 for the y component. So that will be 7 over, once again, the value that we calculated for the magnitude, which is 9.49. So therefore, to get the actual angle, beta is equal to now cos inverse of 7 over 4, 9.49. So just putting that in the calculator, so cos inverse 7 divided by 9.49. So we get an angle of 42.47. So this 42.47 degrees. And then for the y component, so we have cos gamma, and the component for the y here is 5. So once again 5 over 9.49, which is what we got for the magnitude of the resultant. So then we have, therefore, gamma is equal to cos inverse of 5 over 9.49. Back in the calculator. So the final answer for this one is 58.21 degrees. And those are the direction angles, and remember that these describe the orientation of the vector relative to each axis. So whereas for the 2D vector, we only worked out the angle in relation to really the x-axis most of the time. In this case, it's 3 dimensions, so we have 3 angles to sort of contend with here. So that's it for this video. You can check out the next video here on 3D equilibrium, where I do further analysis using 3D vectors.